Welcome to this audio slide where we, the MLCCS, would like to guide you through a structure-function analysis of membrane lipids using extremophilic haloarchaea as our model organism. In the following 4 minutes, we turn the spotlight onto the molecular composition of haloarchaea and showcase how these adapt their membrane to changing and often challenging environmental conditions. At first, please note that in comparison to eukarya and most bacteria, the vast majority of archaea build their cell envelope with a single lipid-based membrane. Therefore, archaea, such as the here investigated haloarchaea, are constantly in need to synchronize their membrane architecture to fulfill its role as protective barrier, but at the same time guarantee an optimum and constant energy supply, allowing these organisms to thrive even within extreme conditions. In this study, we applied state-of-the-art HPLC-MS technology that allows us to quantify the relative abundance of bilayer-forming lipids, or polar lipids, simultaneously with non-bilayer-forming lipids, such as quinones, carotenoids, and squalenes. This technical advancement not only widens our analytical window, it furthermore allows us a direct comparison of membrane-forming versus non-membrane-forming lipids in a single analysis. Based on this HPLC approach, we were able to observe for the first time an extraordinary high fraction of menaquinones in haloarchaeal membranes, reaching levels of up to 72% of the total lipid pool. This ubiquity is the central scheme of our study and raises the question whether menaquinones may function beyond their ordinary role as electron and proton transporter. Therefore, we propose that menaquinones also act as important ion permeability barrier as well as powerful shield protecting the cell against oxidative damage. Furthermore, we provide a detailed molecular explanation of why haloarchaea rely to build their membrane with largely negative charged head groups as well as lipid tails that are highly unsaturated. Although the latter two features of haloarchaeal membranes are well known, a plausible biochemical explanation has to this point not been provided. By combining microbial ecology with detailed lipidomic analysis, we obtained valuable information of how cations, particularly sodium and magnesium ions, interact with different anionic head group species. For example, our manuscript highlights that by bridging two negative charges of adjacent anionic phospholipids with a single divalent magnesium ion, a new kind of lipid is created that, in terms of its chemical properties, closely resembles cardiolipin. In a nutshell, our study provides a bioenergetic perspective as to how haloarchaea managed to overcome a delicate balancing act between great cation impermeability and at the same time enhancing the motional dynamics of the membranes to generate even more energy. We hope you will enjoy our manuscript and would like to get some feedback from you through any of the platforms we use to advertise our scientific activities of the Membrane Lipid Code Cracker Society.